Hey everyone, welcome back, and today let's solve Leetcode problem 1652 titled Defuse the Bomb, the daily Leetcode challenge problem. So we have a bomb to defuse and your time is running out. Our informer is going to provide us with a circular array code of length n and a key k. And to decrypt the code, we must replace every single number, and all of the numbers are replaced simultaneously. So if k is greater than 0, we need to replace the ith number with the sum of the next k numbers. However, if k is less than 0, we need to replace the ith number with the sum of the previous k numbers. And if k is 0, we simply have to replace the ith number with a 0. And as code is circular, again, code is our input array. And since that's circular, the next element of code at index n-1 is actually code at 0. What that's saying is the element basically adjacent to the last index is going to be the initial 0th index. And the previous element of code at index 0 is also going to be adjacent to code at index n-1, the last index in our input array code. So we're given the circular array code and an integer k and an integer key k, and we need to return the decrypted code to defuse the bomb. So in example 1, we have our input array code to be 5713 and our k to be 3. So k is not equal to 0, so we can't just return an array of length n, which is the length of code of zeros, right? We have to actually compute these values, and note that they're actually computed simultaneously. We don't actually do this incrementally, or rather step by step, right? Each number doesn't, one index doesn't kind of depend on the computation of the previous. It's not like dynamic programming. They're all done simultaneously based on how the input array is actually given, right? So we don't have to actually worry about working on computation step by step. It's all done at once based on the elements actually given in code. Okay, so we have 5, 7, 1, and 4, and our k to be 3. And we output an output array of 12, 10, 16, and 13. Why? Because each number would be replaced by the sum of the next 3 numbers. Why is it the next 3 numbers or not the previous 3 numbers? Well, because k is greater than 0. So we want the sum of index I to be we want the value of index I to be the sum of the next 3 numbers after it in our input array code. And so the decrypted code would be 7 plus 1 plus 4. Why? Because at index 0, which is going to be the value 5, the sum of the next 3 numbers are the next 3 indices after it. So 7 plus 1 plus 4. And for 7, it would be 1 plus 4 plus 5, because again, note that this actually is a circular array. For 1, it would be 4 plus 5 plus 7, the next 3 elements after it, because k is 3. And for 4, it would be 5 plus 7 plus 1, right? Because it's again circular. Notice how the numbers actually wrap around. They have that circular effect. In example 2, we have our input array code to be 1, 2, 3, 4, and our k to be 0. This is kind of like our edge case. When we have k to be 0, we simply want to return an array of length n, where n is the same length as our input array code of zeros, right? Because when k is 0, all the numbers have to be replaced by a 0. And finally, for example 3, we have our input array code to be 2493 and our k to be -2. What does that mean? That means we want the elements previous to the index I, because k is less than 0. We want the 2 elements previous or before any index I. So the decrypted code would be 3 plus 9. Why? Because the 2 elements before this 0th index is 3 and 9. And 3 plus 9 is going to be 12. That's why the 0th index of our output array is 12. Then we have 2 plus 3, the previous 2 elements of index 1 at 4. We have 4 plus 2, the previous 2 elements of index 9, which is 4 plus 2. And we have 9 plus 4. Notice how the numbers still wrap around again, even though it's circular. But if k is negative, we want the sum of the previous k numbers rather than the next k numbers, right? And we take, of course, the absolute value of this equation, because we can't actually get -2 previous numbers. We need a whole value and a positive value, that is, to actually get the previous number of k integers. So with that out of the way, I will give you guys a few seconds to kind of just go over this problem in your head and think of a valid solution, and then I'll show you guys how I would ultimately solve this problem in a few seconds. Okay, sorry about that, guys. I realized I was talking a little bit too fast when I was explaining the examples. I'll try to kind of slow it down so you guys can understand. So, for a quick high-level rundown of this algorithm, I'll actually comment down kind of the procedure of the steps of what we're going to kind of do. So, what is the first thing that we should look for? So, the first thing that we should look for, pretty self-explanatorily, is what if k is 0? Well, if k is 0, we don't want to compute any values for any index I in our input array code for our output. Why? Because k is 0. We have a constant kind of result for when k is 0. We just want 0 n's, or rather n zeros, and where n is the length of our input array code. So I'll have a quick kind of edge case there. If k is 0, return an array of length n, where again n is the length of our input array code, with only zeros, because we have to replace every single value with zeros. Like, I don't know if that's how you spell zeros plurally. I think it should be. Pardon me if I'm wrong. But now we also have to make sure that we actually have a result array to populate with actual values, because when we're actually iterating over an input array or any iterable, we don't want to actually change that kind of index or any indices in that iterable when we're actually iterating over it. That's going to create a lot of bugs in our code, right? Rather than bugs, more logical issues, and it's kind of like a rule of thumb when programming. Don't actually modify your iterables while iterating through them. It's going to mess things up, and you're going to get a lot of errors in what you actually want to achieve. So what we're going to do is we're going to actually use a result array to actually populate that and update that, right? And it's going to store our modified values that we actually compute from our input array code. Okay, so now that we have that, now we have to actually extend that array, extend the array to actually stimulate the circular indexing behavior. Okay, I completely butchered that spelling. Stimulate. Don't need that. The circular indexing behavior. So, what does that mean? Notice how when we have something per se, in the first example, like 1, we can't really get the next 3 elements as obviously as you'd like for this index 1, right? Because we can only get really 1 more element without actually going out of bounds, right? So we have to use the fact that our input array code is circular to wrap back around to the 0th index and restart from there to get the remaining 2 next elements that we haven't got from the end of our array, right? Because k is 3. So we have to use that actual circular index behavior and extend our array accordingly. What is that? Our result array. And finally, we need to use a for loop. I'm just gonna write a loop for a little bit more ambiguity if you guys want to solve this yourself after the kind of comments of how to actually solve this for the high-level rundown. We have to use a loop to actually calculate the required sums for each index I. I'm not going to write each index I, I'm just going to write for each index in our input array result, right? Rather, from our input array code to our output array result. So, now that we have a quick rundown of this algorithm, let's just go ahead and straight dive into the code. So, I'm actually going to have my quick base case before I actually initialize my length, right? So, if k is equal to 0, well, if k is equal to 0, we already discussed how when k is 0, we just have to replace every single element in our input array code with a 0. That's very obvious. So if k is 0, we simply want to return an array of zeros times the length of our input array code, which is given as n. And in fact, I actually forgot to initialize n. I'm just going to set n to the length of our input array code, just for easy access when we want to use it later on, like on line 9. Right? We're simply just returning a list or an array of size n or dimension n with only zeros. We're just populating it to be only zeros when our input array k is 0, right? This is kind of just our edge case, right? So we don't actually need any computations to actually compute any indices I and their values, because all elements in the result must be replaced or be 0 as per the problem statement, right? So now that we've actually covered our base case, we can move on to actually computing our real algorithm. So what is the first case here? We have to have a first initial case of, let me comment this out, initial case of positive k value. So if k is greater than 0, what does it tell us? Well, if k is greater than 0, we know that we need to replace the ith index number in our input array code, or rather our output array result for this problem, with the sum of the next k numbers. We don't have to go backwards, we have to go forwards. We want the next indices or values in this array. We want the sum of the next k numbers, that is. So our first case is the initial case of the positive k value. So if k is greater than 0, we can start computing in our result array the actual indices and their values based on the next k elements. So for I in the range n, just iterating over the length of the code to actually help us populate our output array code, we want to set results at that index I that we're actually computing in this index to be equal to the sum of the subarray that forms these next k elements. So how do we actually get the subarray that forms these next k elements? It's going to be code, and I'm going to use some list slicing here, right? It's going to start at index I plus 1, right? We don't want to actually include index I because we want the next k elements. We don't want the elements including that index itself. So starting from index I plus 1, the element after it, up until I plus k plus 1, right? Just the index plus k plus 1, right? The index plus k is going to give us the next k elements, and we do plus 1 because it's exclusive in Python, right? This second parameter isn't actually getting included like for loops are, similar to for loops, so we have to do plus 1 to actually account for that overcount, to actually include that kth index. And pardon me, I actually forgot to initialize my result. Sorry about that. So I'm going to initialize my result to be equal to 0 times the length of our right code, which is just n, right? This is what we're going to be populating. And I'm going to initialize my value code to be code times 2. But what am I actually doing right here? Well, this result is going to be of size n, right? The same length as our input array code, and it's going to be initialized with zeros, and we haven't yet populated it to actually store our final answer, right? And we have to double this code array by just basically concatenating it with itself. We could also do code plus code. Doesn't really matter. I'm going to do code times 2 for somewhat better readability. But why are we actually, concatenating code? Well, we're simply just basically extending this code with itself. Why? Because that simplifies that circular indexing. Why? Because we can just directly access all the neighboring elements beyond the array's bounds, like we saw in example 1. We went out of bounds here, but we can access the next elements because we literally just extended it. And the way we extended it was just concatenating it with itself. So we'd have, let me actually comment this out again. Instead of having just an array of 5, 7, 1, and 4, by concatenating it with itself, we would get 5, 7, 1, 4, 5, 7, 1, 4. And notice how when we have something going out of bounds with the next k elements like 1, we can get the next 3 elements really easily because we just concatenated it with itself. We just went back and got these next 3 elements because we extended with using that circular factor of our input array code, right? That's exactly why concatenating is helpful for this problem, right? We're just kind of getting direct access to those neighboring elements beyond those arrays bounds by just concatenating it and simplifying that circular index with the code array itself. So going back to line 16, where we're computing result at that index I to be the sum of the subarray of code starting from I plus 1, the element after index I, up until I plus k plus 1, right? Which is just the next k elements, right? From the index I plus the index k plus 1 to account for that overcount, because it's going to be I plus k plus 1 exclusive or I plus k inclusive, right? To actually include that final kth element in that subarray of the next k elements. But we haven't actually accounted for the case when k is negative, right? So we've just right now we've just handled the case when k is actually positive. We just summed up the next k elements for each position or index I in our input array code and populated our result at that index I accordingly. But what if k was negative? What if it was less than 0? We accounted for when it was equal to 0 and when it was greater than 0, but we didn't account for when it was less than 0. So I'm going to have an else conditional for that. So else, okay, actually I won't actually indent that. So else, if that's not the case, this basically handles the case where k is negative or less than 0, then we're going to do the same thing but a little bit differently for the previous k elements. So for I in the range n, right, simply just the length of our input array code to actually accordingly populate our result at that index, we're going to set result at index I to be the sum of the subarray of the previous k elements. But how do we get those previous k elements? Well, think about it. We're simply just our index I is going to be the last element, and we have to go backwards from our input array code. And how do we do that? Well, that's going to be code. Again, this is also some list slicing with its indexing. It's going to be from n plus I plus k as our initial index up until n plus I. Right? For each index I in that range of 0 till n minus 1, we're just calculating the sum of the previous k elements. And note, very important, that it's actually, in fact, let me just comment this out as well. Note, very important, that it's the sum of the previous absolute value k elements. Why is it absolute value? Because obviously we can't take the previous of negative elements, right? We can't take the previous negative 2 elements, right? We have to take the previous 2 elements. So absolute value is also very important here, right? Just summing the previous k elements for each position. And we're just offsetting of n to actually ensure that we have proper indexing within our actual extended array when we actually concatenate it with itself, right? The result, or the sum of the subarray of the previous k elements is going to be code starting from n plus I plus k. N is the length of our input array code, I is the current index that we're computing, and k is actually signifying the previous k elements, and it goes up to n plus I. Right, n plus I is simply the length of our input array code plus that actual index that we're at right now. That's basically the ending point of the current subarray that ends at that index I, right? It's simply going to be the sum of the previous k elements, right? And we do n plus I. Why? Because n plus I is exclusive. So it's going to go all the way up, excluding that ith index. So if we had something like 5714 and I was 4, if we wanted to get the previous 3 elements, we'd go from 571. We wouldn't go to 5714 because n plus I is exclusive. So technically this is n plus I minus 1 inclusive, but we don't have to actually get that minus 1 for the next or previous element right to the left of it. We simply can just have 5, 7, and 1. And that's it, we're done. We get the previous k elements up until that index I exclusive. And effectively, once we're actually done populating and actually updating our output array result, we simply have to return the result array after we've calculated and computed every index I for this result array. It's going to actually provide the transformed array as the output of this function. So unless you made any syntax errors here, this should be accepted and this should be a valid solution. And as you can see, this is just about as efficient as you can get. For some reason, it says I'm pretty slow with memory. Probably if I were to submit this again, this would actually be a lot quicker. And as you can see, it is a million times more efficient. It says I now have a 0 milliseconds runtime, and I'm 91% better than most people for most users for memory as well. So these are really just useless, right? Like honestly, you cannot trust these beats slash percent of users on Leetcode. They are honestly ultimately random, but just note that this is the most optimal solution that you can actually get. So to kind of reiterate a quick high-level rundown of how this algorithm kind of works, we're simply computing that circular transformation of our input array code where each element at index I is going to be replaced by the sum of either the next or the previous k elements depending on the sign of k, whether it's positive or negative. But if k is 0, all the elements are replaced by 0, and we simply return an output array of zeros times the length of our input array code for that example, right? We just extend the array for that easy circular indexing as we iterate over all the original indices and calculate the required sum for each position based on the value of our parameter or input k, right? This tells us how many elements to the left or right we have to look for that current index I. So for the time complexity of this solution, this is going to be a big O of n times the absolute value of k. And honestly, that's going to be a little bit hard to actually visualize. So I'm going to actually comment this out and type it manually. So the time complexity, I'll put an equal sign, is going to be a big O of n, right? Where n is simply the length of our input array code, right? It's going to be a linear time solution times the absolute value, like we talked about before, of k, where k is simply the number of previous or after elements that we have to look at for each index I. Why? Because, of course, extending our code, concatenating result with itself, is going to be a big O of n, or linear time operation. And we're also looping through our input array code exactly once for every single index I. And we have to actually calculate the sum for each element, which is going to actually involve iterating over the next k elements, or the previous k elements. And this is going to be a repeated operation for all n indices in our input array code that we actually iterate over our input array code for exactly once. And so this is going to be a big O of n times k solution. N for the actual for loop, iterating through all the indices in our input array code, and k for actually iterating over the k next or previous k elements from that index I, which is going to be repeated. These operations are going to be repeated for all n indices. And the space complexity is actually going to be big O of n. Technically, it's big O of 2n because we're actually extending the array with itself. We have two results, we have two codes and a result, right? But really, it doesn't really matter when we actually concatenate the code with itself, because that's just going to multiply big O of n times 2. But coefficients aren't really important in space and time complexity. They don't actually change the value or the runtime or memory time complexity of this solution. So the simplified, in fact, I'm going to put both. So the time complexity is equal to big O of 2n. Why? To reiterate, extending the array takes big O of 2n, and the result actually takes big O of n. So that's going to be big O of 2n. But the simplified and this should be memory, sorry. But the simplified space complexity is simply equal to big O of n. Because again, coefficients don't really matter in memory and space-time complexity. So the overall memory complexity or space complexity is going to be a linear time solution as well, big O of n. So if you guys enjoyed this solution and learned something new, please consider liking this video and subscribing to my channel. And without further ado, I will see you guys in the next video. Bye-bye.